Section 3.1, Summaries for Symmetric Distributions. So in Chapter 2, we left the ideas of typical values like center and spread very vague. And now what we are going to do is we're going to actually quantify them. We are going to assign them numerical values. There are two different ways to think about the center of a distribution. One way is the balancing point, like the center of mass. The other way is literally the halfway point. The mean is the arithmetic average of a collection of data. This is the balancing point idea of the center. If your distribution is symmetric, your mean will be roughly in the center of your data. However, if it's skewed, it may be off to the right or to the left. Mean, again, mean is just another word for average. So to find the mean or the average, you add up all your values and you divide by however many values there were. The symbol that we use for mean is called X bar, and it's literally an X with a bar over the top. That's the symbol for mean. If we want to give the approximate mean for each of the following distributions, okay, so this first figure, figure 1, we've got SAT scores and their frequencies. Because this is a symmetric distribution, our mean or our average should be right in the center. So I would probably say somewhere right in here at about, I'd say that X bar or the mean is about 1450. However, over here, we've got a skewed distribution. We've got earthquake magnitudes. So we can see we've got a bulk of the earthquake magnitudes kind of in this area here. And then we've got these ones that kind of come off to the edge. And it does even look like we have an outlier out here. So it's not going to be right in the center. Right in the center of these data values would maybe be somewhere over here. However, that's not the balancing point at all. That if I put a fulcrum right here, it would not balance that. So we don't want to do it over there. Instead, I would say maybe the mean, probably if we added all that up and divided, probably somewhere right here would balance it out. So maybe somewhere like 1.8 or even at the 2 would be the mean. So right now we're just estimating them, and we will use StatCrunch to actually calculate those values later. We want to not only use the measure of center, but we want to couple that with the measure of variability to help us understand whether most observations are close to that typical value or far away from it. So we've got mean, that is a measure of center, and then a measure of variability is what we would call standard deviation, that measures how far away the typical observation is from the mean. Here we have the formula for standard deviation. If you had to do this by hand, this is the formula that you would have to do. However, you do not need to memorize this formula. We will use StatCrunch to calculate this. So just showing it to you there to give you an appreciation for what StatCrunch is going to do for us. Okay, here we've got a graph that's comparing exam scores across two different classes. So we've got Class A in light blue and Class B in dark blue, both on the same axis here to compare them. What's the approximate mean for Class A? So if I force myself to only look at these light blue bars, and I want to think what is the mean of those bars approximately, I'd approximately say probably right here in the center, right? We've got a couple very high bars right here and then a lower one on each side working its way down. I would estimate that the average there is probably about a 50. And then if I shift my view and I want to look at this time, I want to look at the dark blue bars, I actually feel as though it probably has about the same mean. Again, if I were to place a fulcrum right there, I think that would balance it out with about the same amount of tall and shorter bars on each side. So I'd say that that mean is also about 50. However, we can clearly tell by looking at these two graphs side by side there on that axis that these classes differed a lot in how they did on these exams. So which one of these classes would we say has the higher standard deviation, and what does that mean? Remember, standard deviation is a measure of variability, how spread out your data is. So the higher standard deviation is going to mean more spread out. I would say that class B has a higher standard deviation, and what that means is that they have more scores that are farther from the mean. So more scores that are farther from the mean. More spread. Okay, in our next example, it says the city of San Francisco has a mean temperature of 65 degrees and a standard deviation of about 8 degrees. The city of Provo, Utah also has a mean temperature of 65, but a standard deviation of 21. So what this would mean is if we wanted to say on a typical day in San Francisco, the temperature is between, so typically we expect between one standard deviation above and below. So we could say between whatever 65 minus 8 is and whatever 65 plus 8 is here. So adding those up and subtracting them, we would get between 57 and 63. The temperature does not deviate very much. It's all centered very closely around that average of 65 degrees. However, in Provo, it looks like they have a much bigger standard deviation here. The temperatures vary a lot more. So to find a typical day there, we would add and subtract again our standard deviation. Would give us that it's typically between 44 and 86 degrees. So very easy to pack for a trip to San Francisco. You could probably wear jeans, t-shirt, sweatshirt anytime there and be comfortable. Much more difficult to pack for a trip to Provo. You might need a coat, you might need shorts because the temperatures deviate so much. Okay, let's see. Which data set would we expect to have the larger standard deviation and why? The finishing times recorded at a marathon or the finishing times recorded at a 100-meter dash? Okay, remember, standard deviation again means spread. A larger standard deviation means more spread. Keeping that in mind, I would pick the marathon here, would have a larger spread or a larger standard deviation, because when people are running a marathon, the finishing times are very far from each other. Some people will finish in a matter of an hour or two. I don't really know much about marathons, but probably within a couple hours. And some people will take many 8, 9, 10 hours plus to finish that. However, in the 100-meter dash, everyone's going to finish within seconds of each other. They're over very, very quickly. So I'm just going to write that down here, that marathons, like marathon finishing times, are very spread out. While 100-meter dash finishing times are all within seconds of each other. So much less spread, much less smaller standard deviation there. Now there's another word you're going to see used a lot, the variance. The variance, we interchange that a lot with the word standard deviation. Variance is actually the standard deviation squared. So if you take whatever number you get for standard deviation and you square it, that is called the variance. However, honestly, we don't use that very much in this class. Standard deviation is preferred for us over the variance, because the standard deviation has the same units as the mean. So